Okay, good evening, ladies and gentlemen. How are you guys doing? As usual, this is the live stream, and I will be looking at my laptop on my left-hand side. And today, what we are going to do is we will go over 15 series, and I have the file in the description. Of course, go ahead and download that. And I don't know if my students are coming tonight or not because they have a test on Tuesday. But anyway, if you're taking Cal 2, hopefully this will also be beneficial to you. If you are not doing series yet, because usually that's the last part, which is usually the last month of the things that Cal 2 instructors do. So if you're not doing it, just come back to this video later on, or maybe I will do another live stream for you guys. But anyway, here are the 15 questions, right? And also we have our secret weapons. And by secret weapons, I mean that these are the things that we can use, and I don't need my students to provide proofs on that, all right? So that's one thing. And the other thing that you guys can find in the description is this. This is my little gift for you guys, which is just a bunch of notes, namely all the series convergence tests that you have to know. The test for divergence, geometric, telescoping, P-series, etc., etc., etc. This is for you guys. Go ahead and go download that. The link is in the description. All right, so it looks like a lot of you guys are here. That's amazing. So 182 of you guys, and so some of you guys are from India. That's great. What time is it over there? Right now it's 9 o'clock p.m. Where I am in Los Angeles time. And let's see. All right, so let's just go ahead and get started. I think the way I'm going to do is I'm just going to post a question, and then I'm just going to see if you guys can answer it or not, and then I will go over it. Right? So here we go. This is the first one. And the question is just, does it converge or diverge? And also you have to provide the reason. So go ahead. Here we have the series, and we have cosine of 1 over n squared. So converge or diverge, and why? Let me see if you guys can. So, okay, Emilio, okay, perfect. Do you remember the 4-digit passcode that I told you in the email? All right. Nobody is giving me the answer. Oh, okay, so I have another Cal 2 student. Okay, I see. Cool. It's not 1590. I don't know who you are, but like, actually, yeah. All right, so let's just get started. All right, so here we have the series of cosine of 1 over n squared. Don't get too excited and just look at the 1 over n squared part. That does not work. Do not be too excited and say, hey, by the P series and this right here converges. No. One thing you have to be good at is you should be good at taking limits of just the AM portion, cosine of 1 over n squared. In fact, if you let n goes to infinity, if you put infinity right here, you get 1 over infinity, which will be 0. Cosine of 0 is equal to 1. So the truth right here is we can actually argue that this will diverge by using the test for divergence. So right here, I'm going to just label the things that we are going to use. Hopefully this right here is as clear as possible. We are going to use the test for divergence, and to do so, we will just first have to check the limit as n goes to infinity of just this portion, namely cosine of 1 over n squared. And of course, you can just show some work if you would like, and perhaps I will just show you guys the work that I saw. Go ahead and put infinity here, so you get cosine of 1 over infinity square, and you see this right here will pretty much be cosine of 0, right? So that will be 1. But anyway, all you have to do is just say this right here is equal to 1. And most important thing is that you have to indicate that 1 is not equal to 0. Do not just say 1 is 1. I know 1 is 1, but do you also know that 1 is not equal to 0? That's really important right here, right? So, because the limit of this guy does not equal to 0, therefore we know this right here diverges by test for divergence. convergence, right? And I know my calculus 2 students are wishing that all the questions are going to be as easy as this one on the test, but that's actually, I don't know, maybe not. But let me just tell you guys though, all of these questions, I actually picked them from my homework. So my Cal 2 students, if you're watching, this is just a good review because, in each section, in the ratio test section, you are just going to do a bunch of ratio test questions. In the alternating series section, you are just going to be doing a bunch of the alternating series tests. But once you have random questions from the homework, the hardest part is what series convergence test do we use, right? That's the most important part. Anyway, this is the first one. And now I'm just going to erase the whole thing and let's move on to the next one. And again, the files are in the description. Go ahead and download it. Hopefully they are beneficial to you. And yeah. Okay, next one, number 2. Here we have the series as n goes from 1 to infinity. This right here looks a little bit intimidating, but doesn't really matter because I will take up you guys. 2 to the negative 3n times 7 to the nth power. So I'm going to look at the chart and see what you guys have. Do you guys have any suggestions on this one? Dr. Payan's here. Oh my goodness. Shout out to Dr. Payan. Go ahead and check him out if you guys would like. Yeah, he has a lot of great math questions and videos, and also linear algebra videos actually. So I see a lot of you guys are saying the ratio test or the root test. Okay. It doesn't really have to be that hard. Alexander, you actually have a very good point, and that's exactly what we are going to do. All right, so here we go. This is question number 2. When we have the series and n starts with 1 to infinity, we have 2 to the negative 3n times 7 to the nth power. Notice that both of them have the n in the exponent. The truth is we can actually do some algebra first, and you'll see we will actually be able to put this into a nicer form. So here we go. This right here, it's the same as the series as n goes from 1 to infinity. This guy stays on the numerator, so we have 7 to the n over this guy, because you have the negative exponent, put that on the bottom. So we have 2 to the positive 3n, like so. Now, if you look at this portion, 2 to the 3n, this is the same as 2 to the 3 and then raised to the nth power, isn't it? Right? Same thing. And then, because the bottom you have the n, and at the top you also have the n, you can put the n to the top, like the following. Look at this as a series as n goes from 1 to infinity. Just give this a big parentheses, and then on the top you have the 7, on the bottom you have 2 to the third power, which is the 8, and then right here both of them have the n, so go ahead and put that down. Now, what kind of series is this? All right, go ahead. When I turn around, be sure you answer, so I am looking at the chart to see what you guys have. It converges? How come? How come? It's geometric. Shout out to Noah, all right? So right here, all you have to do is, because the base is just a number now, and the top is n, all you have to show me is that r is equal to 7 over 8, because this is a geometric situation. But don't just tell me r is equal to 7 over 8. More importantly, you have to tell me that the absolute value of r is less than 1. You have to remember all these little numbers and the inequalities right here. We have a lot of tests, so be sure you download that handout for you. That's for you guys. And in this situation, because it's less than 1, you know this right here converges. And it converges by the geometric series test, right? So, oops, I forgot to write that down first. So right here, I'm just going to write this right here. CONV stands for converges, of course, by GST, right? So converges by the geometric series test. All right, so pay attention to the question. If I ask you guys that, does this converge or not? Fine, we are done. But if the question is asking you, evaluate, that means you actually have to compute the value, if it converges. Because this right here converges, if the question is asking you to give the value, then all we have to do is the following. First, you put 1 in here because you have to get the first term, and we get 7/8. This right here is the first term. And then you divide it by 1 minus the common ratio, which is also 7/8. And then we are just going to go ahead and work that out. You see this is just 7/8 over, this is going to be 1/8. So altogether, the answer is nicely equal to 7. So if you would like, you can say this right here converges by geometry series test, and it converges to 7, right? So this is number 2. All right. And seriously, for all these kind of questions, the more you practice, the more you will be good at. And I know for this test, we have covered a lot of things, all the series convergence tests, and after that, we did a bunch of power series. It's a lot of work, but just 2 more days, and you guys will be done. And then another couple weeks, you will see this again on the final. But anyway, all right, number 3 right here. Here we have the series n goes from 1 to infinity, parentheses -2 to the n, and then multiplied by n factorial over n to the nth power. So this is just a small change from our homework question. But anyway, I would like to see if you guys have any questions, but I mean if you guys have any suggestions on this. If you guys have any suggestion on this question. Oh my goodness, I got a super chat. Thank you so much, Jeffrey. Thank you. And then let's see. Definitely ratio test. And yes, Ivan. Okay, cool. I haven't heard from you in the class. But anyway, you're on my live stream. That's even better. Anyway, definitely ratio test. And you have to remember how the ratio test works, right? So right here, I'm just going to indicate that we'll be using the ratio test. And please do not abbreviate this as RT, because the root test is also RT. But anyway, all we have to do is we are going to check, right? We check as n goes to infinity, and this is just the easier way to do the limit. That way we don't have to write down LIM, right? We check the limit as n goes to infinity, and we have now the absolute value. Go ahead and put this down right here, but you have to do an plus 1, right? So replace all the n with n plus 1. So here we go, we will have -2 raised to the n plus 1, like so, and then times n plus 1, factorial this guy, and then divided by, oh my goodness, n plus 1, and then n plus 1, right? And then we are going to multiply by the reciprocal of this, because remember, we have to check the limit of an plus 1 over an. Namely, we can just do this times the reciprocal of that, which is n to the n, you write that on the top, and over here the bottom is -2 to the n factorial. So we have to work that out. And now, here's the key. It's always a good suggestion whenever you have the factorial, try to use the ratio test, right? So definitely it's a good idea here. So let's go ahead and continue. And the way that you should do it is fix the bigger exponent and also fix the bigger factorial. What I mean by that is, this right here is the bigger exponent. When you do that, you end up with -2 to the n times -2 to the first power. Yeah? What good does this do? Very good, isn't it? This cancel out with that. Very nice. Now we have n plus 1 factorial. Break it down. You write down n plus 1, namely the thing that you have inside of the parentheses, and then you go down by 1. So you have n, but then you go down by 1, it's n minus 1, and then n minus 2, so on, so on, so on. Let's just go ahead and put it down as n factorial. So factorial this guy, and you see, hey, the n factorial cancel out again. Very nice. One more. This right here will again break down the bigger exponent. So here we will keep the n plus 1 raised to the n and then multiply by n plus 1 raised to the first power. The only thing we can cancel is the n plus 1, n plus 1. That's about all, right? So now let's see what else we can do right here. Check this out. Absolute value makes that negative 2 become positive 2. So I'm just going to put down 2 on the top. And then here we have n to the n and also n plus 1 to the nth power. Both of them have the nth power. So I'm going to write it down as parentheses. And here we have n, right? This n over that, which is n plus 1. And then raised to the nth power. Okay, so that's what we have. Now, we still have to take the limit as n goes to infinity. Here is a common mistake. People look here and look here, and they say this right here is equal to 1, right? The limit. I agree. However, the n is approaching infinity. If you just do it like this, you end up with 1 to the infinity's power, which is not determinate. Yeah. This is indeterminate. That means we have to do more work. That means this right here was actually not the way that we have to go. All right, so let's see what we can do with it. This is the moment to take a look at our secret weapons. This is the moment that we can bring out our secret weapon, right? Can you guys see which one shall we use? Which one do you think that we should use? You can do L'Hopital's rule, but that will be overkill. If you guys look at my secret weapons that I have right here for you guys, there's one thing that you can do. It's going to be much better. Yes, Samuel, it's the fact. We are going to be using the fact. And then let's see who else are saying the answer. Oh, a lot of you guys. I cannot keep up with your speed, so let me just write this down right here. Check this out. What we are going to do first is this right here. I'm going to just write it down here, web 2. I'm going to do the reciprocal, and the reason is because if you guys look at the fact that I have for you guys. This right here, I said when we have the limit as n goes to infinity, 1 plus a over n raised to the bn's power, this right here is nicely equal to e to the ab power, right? And this is actually a prime example. Whenever you end up with 1 to the infinity power, it might not give you 1, right? But you know, just keep this in mind. Whenever you have 1 to the infinity power, keep this in mind. It may come out, right? But anyway, you see, we have the n right here. That's why I want to do the reciprocal, so we have the n on the bottom. And to do so, well, I'm just going to negate the exponent, so we have negative n. So that way, I am legally able to term it as n plus 1 over n. Yeah? And now, we'll continue with our algebra. This is still 2, and I'm going to split the fraction. And you see, n over n is 1. And then we have plus 1 over n. And then this is to the negative nth power. This portion is exactly in this form now. And when n goes to infinity, we can just do the following. And you see, right now, I put down the arrow because we are going to take the limit. And if you want to use the fact, go ahead and just write this down. A is equal to 1, and B is equal to negative 1. So you know this part is 2 still, but this whole thing here becomes e to the negative 1 times, sorry, I should put down e to the 1 times negative 1. And this right here gives you 2 over e, right? Because e to the negative 1 power. Okay, so what good does this do? We have 2 over e. Remember, we are doing the ratio test. This right here is actually good because this right here is less than 1. That means we can draw a conclusion, and the conclusion that we can draw is this guy right here converges. It converges by the ratio test. All right? So that's the conclusion that we have after we run through the ratio test. And I believe the ratio test is one of the students' favorite because whenever you have the factorial, that's a really good indicator that you should use the ratio test. And it's a lot of fun to do the cancellation as well. And to make your life simpler, of course, keep in mind the fact, right? So have a look right here. Okay, so continue with number 4, and I hope to finish my live stream within an hour because I don't want this to be too long. And then you guys can check back this week after I gave out the test. I will do the video solutions in the live stream format as well. So number 4. So here we have series as n goes from 1 to infinity, sine of 2n over n plus 3 to the n, right? So do you think that this right here converge or diverge, and why? So I'm going to look at the chat to see what you guys have. Right? Huh. Okay, here's the hint. And in fact, the title of this video is what series test do we use, right? Here's the hint, so keep this in mind. Whenever you're dealing with sine or cosine, and especially the input is like 2n or whatever n, one of the ways to get rid of the sine is to just take the absolute value, because you have to remember, so I'll just put down this. Recall that sine of any angle, if you have this in the absolute value, you can come with a very nice inequality, namely this right here is less than or equal to 1. Right? So it doesn't really matter what you have for the input. Well, here is how we can do it. Even though the question didn't ask us to do so, but again, if you have sine, cosine, if the input is like n or whatever, go ahead and give this a try. So we are going to actually check for absolute convergence. And the reason is because I want to have the absolute value to help us out, because I want to remove the sine or cosine factor. So definitely keep this in mind. Again, if I have this and if somebody replaces it with cosine, we can proceed the same way as well. But anyway, we're going to check for absolute convergence. So what we do is take a look at the series as n goes from 1 to infinity, and you just go ahead and give this guy an absolute value. So boom, boom, and you put the sine of 2n here, and then over n plus 3 to the n, right? So just go ahead and do that. Now, you see that the bottom here is always positive because we just have n plus 3n, 3 to the n. So the bottom is always positive. That means we can just take a look at the absolute value on the top. And then because we know this, so we can actually have an inequality that this being less than or equal to the series as n goes from 1 to infinity. The top, I will just replace that with the number 1. And then divided by, here we have n plus 3 to the n, right? Now, this one right here is actually much simpler to deal with. And what do you guys think? Does this right here converge or diverge, and how come? So I'm looking at you guys again. One over 3 to the n converges, and you see, because you're adding more things on the bottom, so you know you can actually say this. Have a look. You know this right here, it's going to be less than or equal to. In fact, you don't even need to have the equal to, but doesn't hurt when you put down equal to. Anyway, you can actually just remove the positive n on the bottom, and then this guy will still be less than or equal to n goes from 1 to infinity, and write it as 1 over 3 to the n, like this. And if you want to write this down a little bit nicer, well, you can just kind of put the n right here, and you see this right here, it's again geometric because r is equal to 1/3. And once again, don't forget, you should tell me the absolute value of r is less than 1, and this right here converges, right? Because by the geometry series. And now you see this right here converges, and the things that we did, this is smaller than that, therefore this is smaller than that, so we can come back here and say this right here also. Remember, also is a really powerful word. When you have an infinite series that's smaller than or equal to a convergent that you know, you can say that this right here also converges. And the reason here is because by what? Direct comparison test. Right? By the direct comparison test, we know that this right here is less than or equal to a convergent. That means this right here also converges. Right? And now, because we know that this guy converges, you see the absolute value of this guy converges, that means the original one, when you don't have the absolute value, will also converge. Well, this is the reason that you can write down. Once you show all the work right here already, you can say the original guy right here, this right here, converges because it converges absolutely. Right? So this is how you can utilize the absolute convergence test for that. Just take the absolute value, and wherever you end up right here, just try to do any kind of comparison. Usually that's the next move after the replacement with this and also the one. So this right here might be one of the unusual ones, but once you see a few examples on this, and again, try to be good with this kind of inequality, then you will be fine on that, right? So let's look at the next one, and we are also going to be playing around the inequality as well. And let's take a look at the next one. And if you guys have any questions, you guys can leave the comments down below later on. So we will, I will try to answer the questions for you guys later on, right? Okay, let's see. This is going to be number 5. Number 5, we have the series as n goes from, I have 2 to infinity. And then here we have ln n over square root of, no, over n squared. Right? So this is the one that we have. Okay, again, I'm going to look at you guys. What do you guys think? What do you guys think? So Jadon, you said converges by direct comparison test again. That is actually correct. But one thing that you guys cannot do is that you see 1 over n squared right here, right? You see 1 over n squared right here. Do not use the limit comparison test because the version that we went over in class does not apply in this situation, right? So let me just demonstrate a wrong one for you guys first, right? Let me just demonstrate a wrong one for you guys. What if you use the limit comparison test, right? What if you use the limit comparison test? And for the limit comparison test, I usually tell my students that go ahead and put down the things that you know. In this case, we'll just look at n from 2 to infinity and then just 1 over n squared, yeah? And based on this, we can see the p here is 2, which is greater than 1. That means we have a convergent here. That means we have a convergent here. First off, this right here, it's actually bigger than this. So the direct comparison test does not work for sure. But if you try to use the limit comparison test, again, it's not going to work out. Yeah, so I will show you. If we try to do the limit comparison test, what we have to do is we check the limit, right? So we check as n goes to infinity. What we do is we put this, which is ln n over n squared. This is the an portion. again, if you guys look at the handout that I have for you guys, for the limit comparison test right here, right? The limit comparison test right here. And so that's the one. All right. So go ahead and just put down an and then divide it by bn. So I will do that. So divided by bn is just 1 over n squared, right? So let's see what will happen. Well, again, you can just kind of clean up the denominators. You can do this if you would like. And you do the algebra, you end up with ln n, yeah? But as n goes to infinity, ln n also goes to infinity. Now, we have a limit comparison test. This right here is the limit that we end up with. Does this do us any good? You can take a look of the file. You still have 2 more days to study and remember. But if you tell me that this right here is actually bad, that's even better. This right here, unfortunately, if we end up with infinity or 0, the version for the limit comparison test does not work. Right? So unfortunately, sorry, on the exam, if this happens, you just have to erase it and then redo the whole thing again. I know, we have done so much, but this is just life. Yeah. And another thing for you guys is that if I give you guys a hint, go ahead and use it. I did give you guys a hint for this question. So this right here is not too demanding because of the hint, right? So let me show you guys how we can actually do this. When we have the series as n goes from 2 to infinity, we have ln n over n squared. The hint that I gave you guys is that, well, ln n is actually less than square root of n for all n bigger than or equal to 1. This inequality is always true. So we'll be doing what we did earlier. You see here we have ln n, right? Here we have ln n. Well, based on this, we can already say this right here is less than, and if you want, you can put on equal to as well. Doesn't really matter. Go ahead and just write this down as this is less than or equal to, and replace the ln with this. So go ahead and write that down. So you are looking at this as the square root of n over n squared. And this is so much better. Why? Because this right here is the same as saying n to the 1/2 power. So let me just write that down real quick for you guys. And then here we have n squared, and they are just powers. We can just go ahead and work that out. 1/2 minus 2 is negative 3/2. So this right here gives us 1 over n to the 3/2 power. So this right here is actually just the same as the series as n goes from 2 to infinity. And again, all this is just that, n to the 3 over 2 power, yeah? And what good does this do? This is everybody's favorite, namely the p series. Go ahead and circle this, and you see here p is equal to 3/2. But don't just tell me p is equal to 3/2. Here you have to tell me p is greater than 1. Therefore, we know this right here converges, right? This right here converges. And now we have this inequality already thanks to the hint. So we can come here and say this right here also converges. Why? Because we have the direct comparison test. So right here, I'll just write this down for you guys. This is the final result. Converges by the direct comparison test. And the real one that you're comparing with is this. Again, the series of 1 over n to the 3 over 2 power. This is the real one that we are using to compare with, not this. If you use 1 over n squared right here for this series to compare with, it will not work, right? So this is number 5. Hopefully you guys can see after like 2-3 weeks of doing the comparison, the integral test, all the series tests, this right here hopefully shouldn't be too bad. And the purpose for me to go over the homework questions, again, all these pretty much are from the homework, is so that I want you guys to gain the confidence, right? If you have done the homework already, hopefully right now I putting down a question, you say, oh, I remember how to do that. If you have that kind of feeling, you are getting confidence in Cal 2 with the infinite series, and that's the most important part, right? And another thing is that usually on the test, I give 1 or 2 questions directly from the homework just to reward the students who actually pay attention and put in the effort to do the homework. Yeah. All right, number 6. So series as n goes from 1 to infinity, and we have 3n plus 1 over square root of n to the 5th plus 4n square and then plus 12. Okay, so this is what we have. I'll turn to you guys. What do you think that we can do? All right, so I already get the answer. LCT with n to the with 3 over n to the 3 over 2 power. Very good. So here is the deal. Whenever you have a rational expression right here, especially you are just dealing with the powers, right? Here is n to the 1st, and here is technically just powers as well. So n to the 5th, and then the square root, all that stuff. You can try to use the limit comparison test. And in this kind of situation, the limit comparison test works out better than the direct comparison test because it's easier to take limits, and I will demonstrate. All right, so for this one, go ahead and just kind of think of the dominating part on the top, which is that, and likewise the dominating part on the bottom is just the square root of n to the 5. Right here, we are going to use the limit comparison test. Again, let's go ahead and write down the 3 steps. The first step is what we know about the easiest situation. Here is the series as n goes from 1 to infinity. Here we have 3n over just this portion, and we can look at this as n to the 5 over 2 power, right? To the 5 over 2 power because of that square root. All right, and then let's just again work out the power. This is 1, and 1 minus 5 over 2 is negative 3 over 2. So you can say this right here is just the series. N goes from 1 to infinity. We have 3 over n to the 3 over 2 power. And when you have a constant multiple on the top, it doesn't affect the convergence of the series, so you can just forget about it. If you want to be picky, you can put a 3 in the front and then you have the 1 on top. Yeah, it doesn't really matter that much. But anyway, for here, we can say this is again the P series that everybody likes. P is equal to 3 over 2. But don't forget to write down that 3 over 2 is greater than 1. So that means you actually have a convergent series that to be used. All right, now we are going to do the check. The check is we are going to take the limit as n goes to infinity. And I'm going to put down the one that we are trying to do on the top, namely 3n plus 1 over square root of n to the 5 plus 4n squared plus 12. And then we are going to divide it by the one that we know much better. I'm just going to put this down. It's much easier, of course. So I'm just going to write down 3 over n to the 3 over 2 power like this. And now, to work this out, well, I will just put a 3 right here, right? Put a 3 right here. So we have 3 square root of n to the 5 plus 4n squared plus 12. And then I'm going to put this on the top. So you see, I will just multiply n to the 3 over 2 so that they cancel. And then I will multiply this by n to the 3 over 2. When I do this times that, well, we get 3, and then this is n. 3 half, and this is 1, so it becomes 5 over 2. And then this times that is n to the 3 over 2. And the truth is, you don't really have to do too much of this because you're doing the limit comparison test. when you have a rational situation with powers, all you have to do is that pay attention to the highest part, right? The highest power of the top right here. Likewise, you pay attention to this part. And again, this is like the little shortcut that you can take. You don't have to struggle too much, right? So as n goes to infinity, just care about the dominating parts on the top and also on the bottom, and we will get this and that are exactly the same. Yeah, this is that. This and that are exactly the same. So we actually just get 1. And now, we end up with 1. Does the 1 do us any good when we are doing the limit comparison test? The answer is yes. But do not just tell me 1 is 1. Please say 1 is greater than 0. You see, 1 is greater than 0, and the 1 right here is finite, so we can actually draw conclusion. Right? If this is finite and it's greater than 0, we can draw conclusion. We can happily come back here and say this right here also converges, right? They have the same conclusion. This right here converges, this right here also converges by the limit comparison test, right? So if you want to indicate a little word right here, also converges by the limit comparison test. Very nice. And this right here is just like a slightly technical way to argue why that also converges. That's all. Yeah. Okay, so that's number 6. Just 9 more to go, I think. So 10 more to go. Even though I'll say 15 questions, but you guys know, maybe I will have a little bonus for you guys. All right, now number 7, and I'm just going to write this down here for you guys. Number 7, series as n goes from 3 to infinity, 1 over n, ln n. All right, so go ahead and let me know which test would you like to use for this one. Direct comparison does not work out nicely. Yeah, the inequality does not work out. Are you talking about my chart? If you are talking about my chart, it's in the description, right? Ratio test is more useful when you see factorial, right? Okay, I see the answer. Let's see who said that. It looks like it's I think it's integral calculus by your name. And now actually a lot of people are saying integral calculus. Oh, by the way, shout out to King Arthur. I just saw you. Okay, cool. Use the integral test. Why? Because if you imagine this as an integral and replace the n with x, we can totally integrate 1 over x times ln x. So that's the strategy, right? So here we'll be using the integral test. And then now the rest is just the typical write out. So what you want to do first is you tell me the function which you look at 1 over x times ln x, right? You just replace the n with x. And the second thing that you have to tell me is go ahead and provide a graph, right? That's the minimum that you have to do. And when n is equal to 1, you will actually end up with a vertical asymptote. And I will tell you though the graph will look like this. Somewhat like that, right? Somewhat like that. It's not perfect, but yes, somewhat like that, right? All right, so once you have the graph, please mention that f is the 3 conditions. The first one is continuous. The second thing is that f is positive. And then the third condition is f is decreasing, right? For x is greater than or equal to 3, right? This right here is at 1, but we don't care. Anyway, just go ahead and provide this. That's all. And now all we have to do is go ahead and check the corresponding improper integral. So check the integral going from 3 to infinity, 1 over x ln x dx. All right, I don't know, maybe you guys miss doing integrals and you don't, it's back, so go ahead and take the chance for this, right? Anyway, let u equal to ln x, and you see that du is equal to 1 over x dx. And we have done integrals so many times already, so I'm just going to tell you guys the following. remember, these are the x values. When x is 3, u will be ln 3. When x is infinity, u will be infinity. Alright? Here we have 1 over x, which is going to be the 1 over x dx, which is going to be the du. And then we just have the u right here. So we just have to do 1 over u and then du. Yeah? And then you see this right here, if we finish everything in the u world, we get natural log of u. And then we have to plug in, ln 3 here, and then infinity here. And we see this right here becomes ln of infinity, and then minus ln of ln 3, like this. Well, I don't know how big this number is, but I know this is finite. But I also know that this right here is infinity. So you have infinity minus a finite number. You know this right here is equal to infinity at the end. Therefore, this improper integral diverges. So we can come back here and say this right here also diverges. And the reason is because we use the integral test. Right? Diverges by the integral test. So just like this. Right? Cool. And if you are joining the live stream late, don't worry. You guys can watch the replay later on. And again, if you guys leave a comment in the comment section, then I'll try to answer the questions, especially if you are from my Calculus 2 class. All right, number 8. You guys ready? Number 8. Here we have the series as n goes from 1 to infinity, 1 minus 1 over n raised to the nth power. Okay, so you see we have the n in the exponent. Okay, what do you guys think? What do you guys think? What do you guys think? If you do the nth root test, you pretty much will get rid of the n, and you take the limit, and you actually end up with 1, which actually cannot, we cannot draw a conclusion based on that. So the root test does not work. The root test does not work. Okay, I see the answer. This right here, we can use the test for divergence, because again, you have to be good at taking the limit. That's why I gave you guys the three secret weapons for limits. Suppose you just look at this and take the limit. You know this right here is in the form of the fact, right? And we did that earlier as well. So the choice is, let's go ahead and try to use the test for divergence. And to do so, we're just going to check the limit. We check the limit as n goes to infinity. And then we are just going to have 1 minus 1 over n raised to the nth power. Well, for this one, a is -1. So I will put down a is -1 and b is equal to +1. All in all, we end up with e to the -1 times 1, which is, of course, just e to the -1, namely 1 over e, right? And now, you really have to remember, what will this tell you? And we are trying to use the test for divergence, right? So do not say 1 over e is less than 1. We don't want that. When you are trying to use the test for divergence, you have to say that this right here is not equal to 0. You see, this is the best portion. Because if the limit of the an it's not equal to 0, guess what? You are done, I am done, we can move on to the next one. This right here, diverges by TFD. And as I told my students, if you want to create your own t-shirt brand in the future, maybe it can be like TFD, and that would be so cool. I think this is the coolest sounding test that we have. All right, so this is number 8, right? Shouldn't be too bad. All right, number 9. Number line might be a little bit tricky, so pay close attention to this. Here we have the series as n goes from 1 to infinity. Here we have sine square, and then here we have 1 over n. Sine square, and then the input is 1 over n. First off, some of you guys might be thinking, because of what I said earlier, I told you guys, whenever you see sine or cosine, well, sine theta in the absolute value is always going to be less than or equal to 1. Yeah? That's true, but unfortunately in this case, it won't do us any good. If you replace this inequality with that, you will just say this is less than infinity, because you are just trying to say this is less than or equal to the series of 1, which this right here will give you infinity. But we don't know what this is still. Yeah. So too bad. All right, so have a look, and you know I'm going to turn to you guys. What do we do? I see we have LCT with 1 over n squared. Very, very nice. Very, very nice. Badly organized. What's your name? Genius. Right? Cool. And then let's see. And then Marcus. Right. And this right here, if you are doing this for the first time, it might be a little bit tricky, but again, this is actually from our homework. And if you have done similar questions before, you know how this goes. But do not say 1 over n. Do not say 1 over n, right? So anyway, we're going to use the limit comparison test, right? We're going to use the limit comparison test. And let me just emphasize, let me just show you what if you do want to say the series of 1 over n. If you write down, we know that the series of n goes from 1 to infinity. If you just put down 1 over n, well, this right here, we know it diverges. And if you go ahead and check the limit, right, as n goes to infinity, put down this one right here on the top. So we have sine square of 1 over n, yeah? And then put down the one that we are trying to use right here, which is 1 over n. You will see, because we have the square, this means the same as sine of 1 over n times sine of 1 over n. And then we have the 1 over n right here on the bottom, right? Now, as n goes to infinity, sine of 1 over n, this right here, 1 over n goes to 0. Likewise, 1 over n also goes to 0, right? This is the time that we are going to use the limit. Not all the limits can be called the limit. This is the one. Have a look. So just write this down right here for you guys. Well, what does the limit say? This right here is when we have the limit as theta goes to 0. If we have sine theta over theta, this right here will give us 1. Right? This right here will give us 1. Do not do L'Hopital's rule on this. I make a video already, but people still don't want to agree with me, but whatever. Anyway, just write down the answer for this. Anyway, as n goes to infinity, you know that we can take 1 over n to be theta. So I can just write down theta 1 over n, and this right here will be going to 0. So if you look at this as theta, and this as theta, this as theta, well, this part goes to 1 by the limit, but sine of theta, as theta goes to 0, this right here goes to 0. 1 times 0 gives you 0, and unfortunately, when we use the limit comparison test, 0 doesn't do a thing for us. 0 does not do a thing for us. We cannot say this right here, converges or also diverges. We cannot do that. Right? We cannot do that. Well, the truth is, we only have 1 over n. If earlier we had 1 over n squared, this would be a different story. So have a look. We come back here and say the series of 1 over n squared, and in this case, our p is 2, which is greater than 1, and this now is a convergence situation, right? this right here converges. So if this is the one we know, this is the one that we're going to use, I will put down 1 over n squared right here. And then you see 1 over n squared means 1 over n times 1 over n. So the truth is, I will erase, and you see, earlier, this is sine theta over theta, where theta is 1 over n. And now, for the second part, this is also sine theta, and this is also theta. Am I right? Yes, of course. So, for this part, it will also approach 1. And finally, you see, 1 times 1, of course, this right here is just going to be approaching 1. Right? So, this right here will give us 1. Now, does 1 do us any good when we're doing the limit comparison test? Yes. And you have to say 1 is greater than 0 and it's not infinity, so we are good to go. The one that we know converges. This one, the one that we're trying to do, also converges. Why? Because we use the limit comparison test. So show the work, box the answer for the conclusion. That's all. And you can imagine if I ask you guys the series of sine to the third power 1 over n, you just use 1 over n to the third power and you can just break it down this way by 3 times, same thing. All right, so that's number 9. How are you guys doing? Let me know. Are you guys cold? Like, how's the weather over there? It's actually kind of getting cold. I should have put on a sweater. And by the way, I'm purposely wearing this scary Sigma, but not so scary. I try to make it cute. Anyway. All right, number 10. This is a rather hardcore question. Not really though. You will see. 1 to infinity. And 2n factorial over, and the bottom here we have n factorial and then square. Oh my goodness. All right, so let's do this real quick, yeah? We see we have a lot of factorials. Which test we use? Go. All right, Abraham, ratio test. Excellent. So let's go ahead and just do the work. Again, when you see factorial, that's a very good indicator that we'll be using the ratio test. Okay? We'll be using the ratio test. All right, so the check is the following. We check as n goes to infinity. Go ahead and write this as an plus 1. So let's have the absolute value. Parentheses, we have 2. And the n becomes n plus 1. So just do that carefully. So this right here is slightly algebra heavy, but it's not so bad. At least we know what test to do, right? Anyway, this right here is also n plus 1. And then factorial this guy. And then, oh my goodness, square this guy because it says so. Now we multiply by this reciprocal. Namely, we get n factorial and then we square that over 2n factorial. All right, that's what we have. Okay, just like what I told you, go ahead and break down the bigger factorial and also the bigger exponent. So here is the bigger factorial. Let's go ahead and do that. We don't have a bigger exponent. So here we get the inside is just 2n plus 2. Right, 2n plus 2, and then we have to factorial that. Well, this right here is what? To break down 2n plus 2 factorial, we start with the inside, which is 2n plus 2, times the next one, which is 2n plus 1, and then you go down by 1, which is 2n, and then you go down by 1, which is 2n minus 1, and then so on, so on, so on. But you know what? We can just factorial this guy. And you see this and that cancel each other out very nicely. So go ahead and do that. Go ahead and do that. Now, we will also break down this factorial, but we have the power, so do it carefully. n plus 1 factorial, this is the same as saying n plus 1 times n factorial, right? But we have this being squared, so I will actually just square this guy and then square that guy, right? The square for this and the square for that. And again, we see that the n factorial square cancels with this n factorial square, which is very nice. Huh? Pretty good, I would say. And after all the algebra, what exactly do we have? First off, we don't care about the absolute value anymore because we see everything inside is positive. On the top, we just have 2n plus 2 times 2n plus 1. And on the bottom, we have n plus 1 times n plus 1. Right? N plus 1 squared doesn't really matter if whichever way I want to do it. And it doesn't really matter if you want to just do some algebra for fun, you will see that you can factor out 2. So you actually end up with 2 and then n plus 1, and you can cancel this out. Doesn't really matter that much actually. Anyway, 2 times this, 4n plus 2 over n plus 1. Now, finally, I'll take the limit. Draw the little arrow. Care about this, care about that. The limit is approaching 4. Now, we are using the ratio test and we end up with 4. What does this tell us? Right? So diverges, how come? How do we know? Don't just say it's 4. You have to say 4 is what? Because this, so Robert, you got it. So this right here is greater than 1. That is correct. Because this right here is greater than 1, that means this right here diverges, and go ahead and just put down by the ratio test. Right? By the ratio test, and then we are done. Right? So just like that. So have a look. It's not so bad after you just carefully cancel all the expressions and all the stuff. And in fact, the one I assigned for the homework, I just reciprocate this, have this on the top and on the bottom. And in that case, that was actually a convergence. But for this one, I just change it, then it's a divergent. All right, now we did 10 series questions in the sigma form. And then for the next 5, I'm just going to do it with the expanded form. So the first challenge is you have to know how to write it in the form that we need. So number 11, here we have 3 over 5 minus 1 over 5, and then we have plus 1 over 15 minus 1 over 45, and then plus 1 over 135, and then so on, so on, so on. Again, same thing. Converge will diverge, and why? Right, so what do you guys think? So the ratio is, yeah, this is a geometry, right? And let's see what exactly is happening. From here to here, well, the 3 disappears and becomes a 1, and then the denominator stays the same, right? The truth is, from here to here, we just multiply by negative 1/3. And does that pattern hold? Yes, it does. If we multiply negative 1 over 5 by negative 1/3, we actually end up with positive 1 over 15. And then if we do it again, you see that we do have a common ratio, yeah? However, as I said, let's go ahead and just put this down in the sigma notation form. So I'll put down the summation. And let's start with 1, right? As n goes from 1 to infinity. Well, write this in the with the explicit formula. You go ahead and put down the first term, which is 3 over 5. And then you multiply by the common ratio, which is negative 1 over 3. And then raise to the power of n minus 1. Because n starts with 1, right? So that's what we have. Well, right here, you can see r is equal to negative 1/3, but the absolute value of r, which is 1/3, this is less than 1, so therefore we know this right here converges by the geometric series test, right? So technically we are done. All right, let's do this again. What if we want to find out the value of this? In that case, it's the first term, which is 3 over 5, over 1 minus the common ratio, namely negative 1/3. So you see, this becomes 3 over 5 over 3 over 3, and that's going to be plus, so it becomes 4 over 3. Am I right? Yes. And then multiply by 3 over 4, multiply by 3 over 4. Yeah, so finally, this right here becomes 9 over 20. So if the question is asking you what value that it converges to, the answer will be it converges to 9 over 20. Alright, so you guys agree with this answer? I don't know. It's kind of late, so maybe I just did some like fraction mistake. I don't know. Alright, 9 over 20. Good. Alright, so thanks for the people who are participating. Right? By the way, let me know what classes you are taking, where you are from. I do go back to the live stream and then read the chat comments, because right now I want to kind of focus and get everything done. But I usually will go back, especially I'll go back to cut off the videos to show my students. Yeah. Anyway, inverse tangent of 1 over 2. And then we add inverse tangent of 2 over 5. And then we add inverse tangent of 3 over 10. And then we add inverse tangent of 4 over 17. So on, so on, so on. There's one more term on the handout, but I wrote down the question too big. So yeah, the next one is inverse tangent of 5 over 26. Right, so wow. Okay, so what do you guys think for this one? So I have I see someone's freshman from USC. That's cool. And then all right, so take a look right here and let me know, what do you guys think? Converge or diverge? Let me just see. All right, so for this one, go ahead and write down the series. Go ahead and put this down in the sigma notation form, right? This is when n goes from 1 to infinity. Well, you can see that we have 1, 2, 3, 4, 5, and so on. So the top is just inverse tangent of n. But if you look at the bottom, what's the formula for the bottom? We have 2, 5, 10, 17, and so on, so on, so on. So what do we have? Right? What's the formula for the denominator? I'm looking at you guys for help. So go ahead. Okay, Monica, n squared plus 1. Thank you. And allow me to write it as 1 plus n squared for a good reason. Now, how can we test out if this right here converges or not? Well, imagine we have inverse tangent of x over 1 plus x squared. Can we integrate that? Yes. So that's actually doable. Therefore, we are just going to use the integral test, right? So based on this, we are going to use the integral test. I'll just write it down here. We'll use the integral test. And when we use the integral test, first off, go ahead and write down the function, which is inverse tangent of x over 1 plus x squared. And then you go ahead and graph this. But this time, if you graph this, you actually do not have a vertical asymptote. The graph actually looks like this, right? And you really don't care about this part because, in fact, when n is equal to 1, it's right here. And how do I know that? I checked the answer beforehand, of course. But anyway, f is positive, right? F is positive, continuous, and also decreasing for x greater than or equal to 1. So again, please make sure that these three criteria are satisfied before we actually do the integral test. So right here, I'll just put down we check the corresponding improper integral 1 to infinity inverse tangent of x over 1 plus x squared dx, right? All right, so for this one, I'm going to let u equal to the inverse tangent of x. And then du will be precisely 1 over 1 plus x squared dx. So this becomes what? Have a look. When I put in 1 in here, when x is equal to 1, u becomes pi over 4. And when x is infinity, you put it in here, u becomes what? What's inverse tangent of infinity? Pi over 2. Good, right? Pi over 2. So you see this right here, it becomes just u. And then the over 1 plus x squared dx, this portion here is precisely our du. So this is all we have to integrate. And then just go ahead and do that. This becomes 1/2. We have u, and we square that. And then we are going to plug in. We have to plug in pi over 4, and then pi over 2. And you end up with some crazy number. This is 1/2, and then pi over 2 square, right? And then next, minus 1/2, and we get pi over 4 and square that. All right, let me see if I can finish all this. This is going to be pi square over 4, right? And then, so multiply by 2 is pi, and it's 8. This is 16, that is 32, so minus 32 and then pi square on the top, yeah? Good. So I need to multiply by 4 here, So, you know, I want you to finish this. So, all in all, we will end up with 3 pi square over 32. Okay? But anyway, you can have just stop right here because it's finite minus finite. Of course, it has to be finite. But anyway, this right here converges. We go back here. We'll say this right here also converges. Why? Because we use the integral test. So by the integral test, right? So hopefully this right here is clear for you guys. All right. So this is number 12. Have a look. All right. Usually in class, I will say have a look and I'll give my students more time because once I erase, it's erased, right? But if you guys missed it, you can go back. So that's why you want to say have a look and I'll just erase. Okay, so for the next one, number 13. Here we have 1 over 4 minus 1 over 7 plus 1 over 10 minus 1 over 13 and then plus 1 over 16. And so on, so on, so on. Right? So, again, when you have the expanded form, it's a good idea to put it into the summation form first so that maybe you feel more comfortable with it. Okay, in that case, here we go. Sum as n goes from 1 to infinity. Let's just let n start with 1. First thing, notice we have positive, negative, positive, negative, positive, negative, and so on. Therefore, this right here is alternating. And because the first term is positive, that means we actually have to have negative 1 raised to the n minus 1 power. This factor will make the first term positive, right? And then it will make the rest of the terms alternating. Now, 4, 7, 10, 13, 16, every time we just add 3, right? So this is how you can do it. Because the bottom here is arithmetic, you know it's going to be linear, namely a number times n to the first power, and that number is precisely 3. 3n, right? The common difference is the coefficient of n. Now, when n is equal to 1, you put it here, 3 times 1 is 3, and you ask yourself, 3 plus what will be 4? 3 plus 1 will be 4. So the bottom is just plus 1 right here. Just like that, right? So this is the formula for that. And now, you see, we do have a negative 1 to the n minus 1 power. Which test do you think that we can use for this one? So I'm looking at you guys and let's see what test. Okay, Rodrigo, we are going to use the AST. That is correct. So if you would like, you guys can rewrite it. N goes from 1 to infinity. Write it as negative 1 to the n minus 1 power, and then you multiply by 1 over 3n plus 1. Yep. Okay, for this right here is our Bn, right? And here we are going to use the alternating series test. So go ahead and do our usual business. First check the limit as n goes to infinity of Bn. Well, this is the same as saying the limit as n goes to infinity of that, which is 1 over 3n plus 1. You put infinity to here, we get 0. So the first criteria checked. Now, second one, we need to see if Bn is decreasing or not. So Bn plus 1, is this less than or equal to Bn? I don't know yet, so let's put it on a question mark. But we know it will work. Anyway, this right here is the same as saying 1 over 3 times n plus 1 and then plus 1. Is this less than or equal to Bn, which is just the original? Well, of course it is. And just have a look. If you guys would like, you can cross multiply. This becomes over there. So it's 3n plus 1. Is this less than or equal to this times that, which is 3n, right? Plus 3. Plus 1, which is plus 4. So this is, of course, true. This is, of course, true. So we have these two criteria being checked. So we know this right here converges by the alternating series test. Right? Just like that. Not so bad. Right? Not so bad. Okay. 2 more. And yeah, it's about 1 hour and 30 minutes. Okay, so 15 questions and some interactions. That's about okay. Next one, right? Next one. Number 14. 1 over 3 plus 1 over 8 plus 1 over 15. And then 1 over 24. And 1 over 35, and so on, so on, so on. Okay, so turn to you guys. How do we do this? Okay, then you got it right. It's 1 over n times n plus 2. Very nice. So again, when you have the expanded form, go ahead and put it in the summation form. Have a look right here. 3 is the same as 1 times 3. 8 is the same as 2 times 4. 15 is the same as 3 times 5. And this right here is the same as 4 times 6. And this right here is the same as 5 times 7, etc., etc., right? Well, this is the sum as n goes from 1 to infinity. And everybody on the top is just 1. And if n is equal to 1, we have this, right? So it's just n. And this right here is 2 more than that. This right here is 2 more than that. So we have n times n plus 2. All right? So now, this is perfect. We can multiply this and we get n squared plus 2n on the bottom. And we can do some direct comparison or limit comparison. You know this right here converges. But for this particular situation, we are going to do a little bit more work because we can actually figure out what this converges to. Because this right here is a telescoping series. So, ladies and gentlemen, what we are going to do is we will take the advantage of doing the partial fraction right here, and you will see we will end up with a telescoping series. So, some number over n plus some other number over 2, n plus 2. Well, to figure out this number, we go back to the original, we cover this up, and we have to let n equal to 0, and we put 0 right here, so we get 1/2. Yeah? And then, to figure out this number, we go back to the original, we cover up the same denominator, n plus 2, and we have to let n equal to -2. But put it here now, so we actually end up with -1/2. Right? So that's what we have. Now, have a look. Both of them have 1/2, so we'll actually just factor that out. And have a look. 1/2, and we have the sum, n goes from 1 to infinity. And then we have 1 over n, and then minus 1 over n plus 2. Yeah? And you see, they are subtracting, and this and that, they are of the same kind. So this is the indicator that this is a telescoping series. So let me just write this down right here. This is the telescoping situation. And I'm just going to do the short way, the super way to do this, right? Here we go. We have the 1/2. Go ahead and just put that down all the way in the front. And actually, I still need some space in the front. So let me actually just put down 1/2 right here. Let me ask you, this is n plus 2. They are off by how many terms? Well, n and n plus 2, they are off by 2 terms. If they are off by 2 terms, you can just do the following. Go ahead and put in the first n value here into this expression. So put a 1 in here, we get 1 over 1. That's the first surviving term. And the next is when n is equal to 2. You put 2 in here, and you get 1 over 2. So just draw in the first 2 numbers into the first piece, and then you will just add them up, right? That's pretty much it. And then you also need to subtract the last 2 terms from here. And let me show you what I mean by that. Go ahead and just put this down, which is minus 1 over n plus 2, right? But we also need to have its previous term. 2 terms in the front, 2 terms at the end. So here we go, minus 1 over n plus 1. The previous term, like that. Okay, then once we have this, we're just going to go ahead and take the limit as n goes to infinity of all that. And the reason why is because this right here, it's actually the nth partial sum formula for this series. So when we take the limit as n goes to infinity, we will actually be able to find out the sum of this series. Well, the good thing is, when n is approaching infinity, this guy goes to 0, and likewise, this guy also goes to 0. So now, all we have to do is 1/2 times 1 plus 1/2, and this is the challenging part. Let's see. This right here is going to be 3 over 5. No, what am I talking about? This is 3 over 2 times 1/2, which is 3 over 4. Right? Yeah. Okay, so good? Are we good? Are we good? All right, so when you have this and that, if they're off by 2 terms, right? N and n plus 2, they're off by 2 terms. The fast way to do this is that you see the starting n value right here is 1. And then the next n value is 2. You're drawing this here, and you're drawing 2 in here, so you write down 1 over 1 and plus 1 over 2. You have to have 2 terms in the front, right? 2 terms in the front. And then this right here, go ahead and just write it down, because that's going to be the ending part. But you also need to have its previous term. Why? Because 2 terms in the front and 2 terms at the end. And we still have the 1/2 right here, right? So the way to do it is you just draw in the numbers and you'll see the cancellations, and these guys will be the surviving guys. And I do have like complete videos on this kind of things. Again, this is more like just a review for you guys. But hopefully this right here is clear enough for you guys, right? Okay, cool. So I just wanted to have some confirmation. This right here is 3 over 4. Because I don't remember why I did a question, the answer was 5 over 12. But I thought I put that question on the handout for today, and I haven't seen any questions with 5 over 12 for the answer, so that's why I'm like kind of, what am I doing? But anyway, I think that's correct, and yeah. Okay, one more question, right? Just one more question. Here we go. Number 15. Last question right here. We have 1 plus 1 over 2 to the ln 2. And then 1 over 3 ln 2. And then 1 over 4 ln 2. And then 1 over 5 ln 2. Like this. And then so on, so on, so on. This right here, it's not so bad, so I'm just going to go ahead and proceed. First off, put this in the summation form, n goes from 1 to infinity. And everybody on the top has 1. So I'm just going to put down 1 right here. And you see, this is technically the same as saying 1 over 1. And can I write this as 1 to the ln 2 power? Yes, 1 to the ln 2 power is still equal to 1. So you see, the base right here is just going to be n. And then the power is just going to be ln 2. Is this series hard or easy? It might look weird, but it's actually pretty easy because it's just a p series. You see, here the p is natural log of 2, which is approximately 0.693. And don't just tell me p is equal to that, but please tell me that this right here is less than or equal to 1. Therefore, we know this series right here diverges by p series. All right, so with that, we are done. Hopefully, for the people who are actually watching this, especially for my students, hopefully you guys find this helpful, and hopefully you guys gain some confidence, because this is maybe your second or third time of seeing these questions, and you feel better about doing infinite series, that, right? And you guys know I usually like to give you guys a little bonus, especially for this one, just like a little question for you guys. Right? For my Cal 2 students, you don't have to worry about this one. It's just question for fun. This is a slightly harder one, right? So I will say. Anyway, converge or diverge, right? I think I should write down the question for you guys. Bonus. Converge or diverge. And the question is, of course, we have the series as n goes from 1 to infinity. Well, this is the last question I'm going to put out. So let me just talk to you guys. So just kind of answer your questions in the chat. If I have the series as n goes from 1 to infinity of cosine of 1 over n, does this converge or diverge? Go. This right here diverges. How come? Because if you take the limit of cosine of 1 over n, if you take the limit of that, that goes to 1, which is not equal to 0, which you can just use the test for divergence for that, right? So yes, if you just have this right here, diverges, very nice. But what if we have a 1 minus that? Now, if you want to use the test for divergence, 1 minus 1, that will actually give you 0, so the test for divergence does not work. Does this diverge? Does this converge? Well, don't just tell me converge or diverge on the test. This is not just about a 50-50, all right? It's not just you put on converge or diverge and then you're allowed to move on. No, it's not like that. You will also have to provide a reason for that. So what do you guys think? And you know what? In fact, I'm actually not going to work this out. I'll give you guys some hint though, if you guys would like. I'll give you guys some hint. Alright. Let me see. How should I give you guys the hint? Anybody has the answer for it? Anybody has the answer for it? Let me see. Again, I'm not looking at if it converges or diverges. I'm looking for the reason. Oscar, how are you doing? Well, if you say by comparison test, you will have to say compare with what, right? As I said, this right here, it's not so easy, right? It's not direct. You don't do the series with 1 over n, that does not help, right? So I would just say, if you compare with the series of 1 over n, if you do that, unfortunately, it does not work. Does not work. It does not work. Right? It does not work. And if you well, test for divergence in this case, again, doesn't work. Doesn't work for that. And what else do I have to tell you? I am going to remind you guys of trig identity. Right? This right here might help. And it's actually, once you use the trig identity, it's similar to one of the questions that we did earlier. One of the trig identity is that if you have sine square theta, if you have sine square theta, this right here, it's equal to the part that's going to be 1 minus cosine something. And that's why I bring this up, right? If you look at sine square theta, this right here is 1/2 times 1 minus cosine of 2 theta. This right here can do you some good. And after that, you should be able to see which series that you can use to compare, right? So go ahead and just work this out, and you can send me the answer, or you can tweet me the answer, or whatsoever, or maybe you leave the answer in a comment. But anyway, that's it for tonight. And let me see if I can just see some of you guys. No, it's not sine of infinity. It's not like that. Right? It's not like that, because remember, theta is actually, you have to look at theta. It's not just, the theta is here, right? 2 theta, you make it equal to 1 over n, just like that. But anyway, that's it for tonight. And again, hopefully all this helps. And if you guys would like, I can do more for this. I can do more series for you guys. Right? So that's it. See you guys next time. Bye.